All right. Are we all ready? Welcome back. Thank you for coming back. Today I'm going to tell you something about fixed points in digital topology. This will be completely different from what I talked about last time. I'm still glad to be here. Here's a picture of us at the... Oh no, sorry. Come on. All right. I saw this in Professor Kumam's tweet. Yeah, so this was at the airport. Yeah, so I'm still glad to be here. Thank you for being here still today. Again, I will say, please interrupt me with questions. No algebraic topology today, so it should be more understandable to everybody, I hope. But please let me know if you have questions. In my opinion, the digital topology is easier to understand than what I was talking about last time, I think. What we want to talk about in digital topology is set like this. This is a digital picture that I made a few years ago as just a sort of happy little guy. And we would like to consider shapes like this. Consider this as a finite set of pixels. Each little square is a pixel. And there's finitely many there. And we consider this as a subset of Z2 because they sit on integer coordinates in the plane. If you want to study this topologically, you can't really treat it like a topological space. We can't use the subspace topology from R2 because this is a finite set. And topologies on finite sets are not very well behaved. In particular, if you know some topology, there's a theorem that says the only Hausdorff topology on a finite set is the discrete topology. And if you want to use the subspace topology from R2, you just get the discrete topology, which is not useful for making continuous functions or neighborhoods or anything like that. So we are not going to use any topology at all, really. We require a special kind of theory to think about shapes like this. So that's what we're going to talk about. I think it's an interesting time for the field of digital topology. It started in the 1970s, so it has been around for a little while, but not a lot of people are working on this kind of thing, which I'm going to describe to you today. It's me and Sirajo. No, there's some others, but not many. Actually, a lot of people do mathematics with digital images, fancy image analysis. All of that kind of stuff, that kind of digital analysis, digital image analysis is generally very applied. And the idea is you want to do certain specific things with real, pictures on a computer somewhere. Things like compression or feature recognition. You want to recognize people's faces in a picture or something. Many people work on that, and they make more money than I do. Maybe some of you guys work on that kind of thing. But in the mathematical field of digital topology, the goal is to build a topological theory. Oh, this is a mistake. We want to building. That's bad English. We want to build a topological theory and to prove theorems about things like this, all right? This is different from trying to make some algorithm that does something, right? We want to actually prove some mathematical theorems. Here's a little historical example about the difference between proving theorems and actually doing things. Maybe you recognize this. This is like the bucket button that you see if you ever use Photoshop or something. Do you know this thing? You click it and it fills in the region with a color or a pattern or something like that. The bucket fill button, it fills the inside of a region. And this, I did some research on this. I think this was used first in the 80s on Mac Paint, which was something that was included with the original Apple computers. And it works, mathematically speaking, because of the Jordan curve property in R2. This is something you might know about. It's just a theorem. It says that every simple closed curve that is a loop in the plane which does not intersect itself, every such curve divides the plane into two regions, the inside and the outside. All right, this is the Jordan curve theorem. And it sounds very simple, but it's actually not very easy to prove. But anyway, what it means is when you click the bucket, there is an inside. This the theorem says. There is an inside, and so the bucket can work. All right? But the Jordan curve theorem that I just said is actually not really true in Z2. It is true in R2, but in Z2, here's an example of a set of pixels in Z2. And if you notice, this right here is a simple closed curve, like in the Jordan curve theorem. It's a loop which does not intersect itself. But you will notice that this does not divide the plane into the inside and the outside. Actually, there's two insides here. All right, so the theorem is not even true, which makes the bucket work. So how does the bucket work? Well, it just works. It's a silly question. This region has two insides. All right, so there is a digital version of the Jordan curve theorem, which is a little different from the classical version, and it was proved by Kalimsky and some other people. This was like in the 1990s. But I'm trying to give you an example where the application, that is the bucket, the button existed before the theorem was proved, right? And the people who invented the bucket, they didn't care about the theorem. They just made the bucket to work. So the application actually came before the mathematical theory in this case. Actually, this is something, I don't know if you care about this. This is a little historical discussion. This was actually a usual thing in mathematics before the 20th century. It was very common that the application comes before the theorems. Everybody knows actually this happened in calculus. This is a famous mathematical historian talking about the derivative. She writes that first the derivative was used, then discovered and explored and developed, and only then defined. The definition, the actual definition used in calculus came much later than the people who invented the basic idea. All right, so like the idea of a limit is very old. The old philosophers talk about limit, but it was not actually given the real definition, the epsilon delta definition, not until the 1800s, which is 100 years after the calculus was invented using limits, even though they didn't actually understand the limits. So all of this to say, the applications come first, and then the theorems come later. That's often how it goes. And this is what is the situation right now in digital topology. We are proving a lot of theorems, even though very, very sophisticated applications already exist, but the theorems don't exist yet. So that's what the study is about, and I think it's interesting. So let's talk a bit about it. I will call this Rosenfeld style digital topology. There are many different models of digital topology, and the one that I know about, I actually don't know very much about all the different ones. The one that I am a bit of an expert in is based on Rosenfeld. Siraj had a picture of him. He has a paper called Digital Topology, which gave the basic definitions that we're going to use here. So in this model, we only care about the pixels and their adjacencies. Which one is next to which one? And we don't care exactly where the pixels are in the plane because we want to be topological rather than geometric. So we don't care exactly where they are or which direction the adjacencies go in. I'll show you an example. So in digital topology, these are all the same. You can see there's some differences. Like here, the arm goes down, but here it goes up. But topologically, it's the same. They're geometrically different, but we want to consider them to be topologically the same. And this over here is just a rotation of this one. So again, we don't care, in the topology, we don't care about rotation. This one, though, this one is actually different topologically because now this is disconnected. If you cut it, then that is going to change the topological structure. So this is how we want to create our theory. We want to invent some definitions which make these all the same, but this one different. The Rosenfeld approach is to view every digital image as a graph. So This one, actually, there's two different ways that you could make this into a graph in a natural way. And here are some pictures of that. The difference between these two is just about the diagonals. Do I consider two things to be adjacent if they are diagonal, or only if they are next to or on top of each other? So, and there's for certain settings, it's better to do this way. Sometimes it's better to do this way. There's no best way. This is different from in like topology in the plane. There's like the standard Euclidean topology. There's not in digital topology. There's different ways that you can do it, and these are very different topologically. Like this one here, you can see is disconnected, but this one is connected. So it really matters. It makes a big difference which one you use. Formally, here's the definition: a digital image is a pair x comma kappa. X is a set in Z2. Now, usually we consider only a finite set, but some people have written some things about infinite sets. And also this Z2 really doesn't need to be Z2. Z2 is the most common setting, but you can do this in Z3 or higher, or Z1 if you want something very simple. Kappa is a symmetric and anti-reflexive relation, and it's called the adjacency relation. And choosing, like I said before, choosing different adjacency relations will give you different things topologically, like these two. I said this already. The one over here is connected, but this one is not connected, so it makes a difference. There's names for these. Siraj talked about this also. There are actually many different names used by different authors, but I'm going to call this one C1 over here, and this one C2 over here. And the names, so this I'm going to write like this. X is adjacent or equal using C2 if the coordinates differ by 1 in either position. This is how you get that diagonal or side-to-side adjacency. Whereas the C1 means their coordinates differ by 1 in one coordinate, and they are equal in the other coordinate. So C2 is the one with the diagonal. C2 is the one that's only straight adjacencies. And then you can do these in higher dimensions, not only 2. You can define CK means they differ by 1 in at most k positions, and they are equal in the other ones. So in Z3, you get 3 different ones. There's C1, C2, and C3. And C1 has no diagonal. C2 allows face diagonals on cubes. So on a 3-dimensional cube, you can go diagonally across one of the faces. That's allowed for C2. And then C3 also has a diagonal which goes across the middle of the cube. So that's what these look like in Z3. And in higher dimensions, you have the same idea. All right, so the big idea generally is to try to copy our favorite ideas from classical topology and see if we can do the same thing in digital topology. Or you could try to define something which is purely digital. That is something which only makes sense for digital topology. This is, in my opinion, this is a little more interesting to come up with completely new ideas and new invariants. Although it's a little harder because you have to have some really new idea. It's pretty easy to do this kind of thing. You get your favorite topology book, and you just try to copy everything into digital. And it's a little harder to come up with these purely digital ideas. All right, some of the ideas in classical topology are interesting when you try to copy, and some of the ideas are not interesting when you try to copy them. And I'll try and show you some examples. We're always looking for things which use the digital structure. This is sometimes you can think that you've discovered something new, and really it's not. We don't just want theorems about finite sets. There are many things which are true just because it's finite, but that's not very interesting. We want something that is actually true because of the digital structure of the thing. Okay, here's one big idea that doesn't work very well. Open sets. I said before that we don't actually use real topology. So there's some people who say, oh, digital topology is not even topology. And that's kind of true because we don't use open sets or any of that kind of stuff. There's no natural topology to use on a finite set, so we're not going to define things in terms of open sets. People do talk about neighborhoods sometimes, but they're much less important than they are in traditional classical topology. No open sets, but you can still talk about continuity of a function, and this is a basic thing that we need if we're going to do topology. So this is the definition of a function being continuous. So if you have a function from x to y, these are 2 different digital images. Continuous means whenever A is adjacent to B, in the domain, then when you do the function, you get points which are adjacent in the codomain, in the image. All right. So if that's true, then it's called continuous. Equivalently, you could say this way: f is continuous when the image of a connected set is connected. And this is one thing which is true in classical topology. So you could write it this way if you want it to sound the same as the classical continuity. All right, this is how we define continuity. And you can prove, it's not hard to show that like a composition of continuous functions is continuous, and all the properties you want are true for this. So if you would like to draw a graph of a function, it would look something like this. This is a continuous function. So what it means to be continuous: when you have 2 points which are next to each other down here, then the 2 things should be adjacent vertically. That's what continuity means in this case. So everything will be connected like this. You cannot have, well, the slope cannot be very much in a function like this to be continuous. Because if this point was up here, then it's too far away to be adjacent anymore. All right, this is what a continuous function z to z would look something like that. Let's talk about some very basic ideas that we talk about often. A digital interval is something like this. Some interval from a to b intersect with z. So we only talk about the integer points in the digital interval. We'll write it this way: ab with a little z down there. And a digital interval, we always use C1 adjacency. That just in the dimension 1, that's the only one which really makes sense. The number is adjacent just to the one that's greater and the one that's lesser. Digital intervals, this is one difference from classical topology. Digital intervals are all different. For example, the interval from 0 to 1 is different from the interval from 0 to 2. There's no bijection from one to the other, even though in classical topology these are homeomorphic. But in digital topology, they're not. There's a difference. This is something that is sometimes causes some problems. Here's one classical concept which is not interesting in digital topology. It's the fixed point property. I said I was going to talk about fixed points. It turns out not very interesting in digital topology. And Siraja mentioned this. The fixed point property, we say X has a fixed point property. It means every continuous map X to X has a fixed point. As you know, in classical topology, we have the Brouwer fixed point theorem. It means every classical interval or a disk has a fixed point property, and there are many other spaces which have the fixed point property. What about in digital topology? Does a digital interval have the fixed point property? Actually, it doesn't. Sirajo gave a little example yesterday of a continuous function on an interval which has no fixed points. So we all know the answer is no. I was going to show this picture here. Here's a self map on the interval 0 to 3. So we have 4 points total. That's 0, 1, 2, 3. And then we also have 4 points in the codomain. And to find the fixed points, you can look for intersections with the diagonal line. And here you will see there is no intersection. Like these lines cross, but that doesn't count because there's no point there. So there is no intersection with the diagonal. The little lines don't count. That means there are no fixed points of this function. All right? So a digital interval does not have the fixed point property. You can always make an example like this. It's not so hard to do. I say, unless A equal B. If the interval only has 1 point, then it has a fixed point property. But that's the only example. And Siraja said there's a theorem that says the only digital image with the fixed point property is a single point. So basically nothing has a fixed point property. You might look and say, well, those lines, they cross, so maybe there's not a point there, but that's something should be true about that. Yeah, actually, for the interval, this must always happen, that it will cross over because of the Brouwer fixed point theorem. It means if you have no fixed points, like in this case, since there's no point right there, still it is true there will be points with f of x adjacent to x, because when this crossing happens, which it must happen, either there is a point right there and there's a fixed point, or there's no point there, but these ones will always be adjacent to each other. So if there's no fixed points, there will be some points like this. F of x is adjacent to x. That's what I just said. Even though it doesn't have the fixed point property, it has this property. There's some point like that, adjacent or equal to x. And this is called the approximate fixed point, when f of x maybe is not equal, but is next to x, adjacent to x. So we say a digital image has approximate fixed point property when every continuous self-map has some approximate fixed point. All right. So an interval does not have the fixed point property, but it does have this property, AFPP. This is what I said before. No non-trivial digital image has the fixed point property. Oh, here's a little proof. I don't know if Siraj talked about this. It's not hard to see why this is true. If you just start with the constant map on any digital image, the constant map has one fixed point. Wherever the constant value is, that's the fixed point, and no other point is a fixed point. If you start with that, but then you change it so that f of c is some other point which is adjacent to c, but everything else is still equal to c, then this has no fixed points. And this construction works for any digital image. So, and it's going to be continuous. So that's why, yeah, no digital image has the fixed point property except just at one point, which is not an interesting example. Many digital images have the approximate fixed point property. Actually, this is something that I think no one has really studied in detail. And it's something, it's not because it's too hard, I think just because nobody has studied it. So if any of you are interested in looking at this, this is a very general question, but which digital images have the approximate fixed point property? The interval does, because we just said so, but what else is not much is known about this. And again, it's not because it's too hard, I think just because nobody has really thought about it. So something to think about. Interval does have approximate fixed point property. This is a cycle of points. This does not have the approximate fixed point property because you can make a function which just rotates all of these points by 2 positions. And then there's no fixed point and also no point which is adjacent to its image. So this has no approximate fixed point. So this kind of thing, and not just this size, but even if it's bigger, this has no approximate fixed point property. This little guy I call Pappy. My kids gave it a name because they saw me working on this once. Pappy does not have the approximate fixed point property. That's because I can find some function which does not have an approximate fixed point. Here's how you do it. I say map all the points down to the lips. The lips are like around the mouth there, those white points. So you make all the points go down to the lips, and then you rotate the lips, all right? And you have no approximate fixed points of that function there. Rotate by 2 positions. If you go only 1 position, then everything is approximate fixed, but if you go more, then it's not. All right, here's a conjecture. This is not like a famous conjecture. This is just what I think might be true. If x is finite and has a big loop, I mean like the lips or something like that inside, then x does not have the approximate fixed point property. I think if you have inside some lips somewhere, it's always possible to map everything down and then rotate. This I think is probably true. I'm not sure. What I mean by big loop, I mean probably length 5. If the loop is too small, then there's not enough space to rotate it to remove the approximate fixed points. And of course, by big loop, I mean not a contractible loop, a loop which has like empty space inside. Probably this depends on the adjacency you use. I don't know if this is always going to be true. And yeah, it might just be false. I don't know. It would be interesting to think about the converse. If x does not have the approximate fixed point property, does that mean automatically there must be a big loop inside? I don't know. Yeah, this would require it to be connected. If it's not connected, you can just like swap the two components, and that will have no approximate fixed points. But yeah, this is an interesting question that if any of you are interested in, let me know. We could think about it. It is necessary to be finite. Here's an interesting example. If you take all the integers z, this has no big loop, but it does not have the approximate fixed point. You can just shift everything over, and it will have no approximate fixed points, even though there's no loops for the lips. But so this finite must be necessary, but I don't know why exactly. All right, here's something that probably most of you are familiar with, the Banach fixed point theorem. There is a digital version of the Banach fixed point theorem. So this is another thing that you can try to copy the original proof into the digital settings. This was done in 2015 by these guys are very, they have many publications in digital topology. If you assume that, so to do Banach fixed point theorem, you need a metric. So if you assume x, they say x is a digital metric space, it just means a digital image, which also is a metric space. And they have this contraction condition, which if you're familiar with the Banach fixed point theorem, this is the same. You say F is digital contraction when this is true. It just means all the images of all the points are going closer together. And the theorem looks like this. When X is a finite digital metric space, any digital contraction map has a unique fixed point. It's exactly like the Banach fixed point theorem. And if you read the paper, the proof is exactly like the same proof. No modifications necessary at all. Something that you realize, though, when you read the proof, this is not a digital theorem at all. What I mean by that is, X is a finite, you assume finite digital metric space. But even if we take away the word digital, it's a finite metric space. Every finite metric space is a complete metric space. And so you already have the original Banach fixed point theorem, which you can use. The digital is not necessary at all right here. The classical Banach fixed point theorem applies because it's a finite metric space, and you get the same unique fixed point. That's why I say this theorem is maybe not truly a digital theorem. It's just a theorem about finite metric spaces, which already has the Banach fixed point theorem. In fact, this is true in general, at least as far as I've seen. I haven't read every paper about digital topology, but as far as I have seen, metrics generally don't work very nicely with digital images. So here's an example that I think was suggested by Boxer. This is a paper that I have with Boxer. I think it was his idea, though. If we have 3 points here in Z5, this is a little strange example, but 3 points in Z5. One is the origin, one is this point, all ones, and then this point with a 2 and then zeros, all right? If you want to draw a picture, it's like this. This is in Z5, so this is like out in Z5 with 1 on all the coordinates, all right? 3 points, and I'm going to use the C5 adjacency. That means all the diagonals will be useful as adjacencies. So these points are, P0 and P1 are adjacent because all the coordinates are at most distance 1 apart. And then this and this are adjacent because, again, all the coordinates are at most distance 1 apart. So it is connected here. Those adjacencies go like that. But look at the metric. This is strange. If you use the Euclidean metric, then the distances between these 3 points, this is 2. These are root 5 each. It's because you do the square root of the 1 plus 1 plus 1 plus 1. So you get the square root of 5. And the square root of 5 is greater than 2. It's not clear on this picture, but so these ones are actually longer than this one. And I can make a function here which takes the, so this function will send the origin and this one over here both to itself. So P0 and P2 go to the origin, and f of P1, this one goes to P2, all right? This is not, so this does satisfy the contraction condition that's used in the Banach fixed point theorem. If you just look at all of these distances, they all decrease when you do this function to them. So this root 5 becomes 2, which is less. And this 2 becomes 0, which is less, all right? So this is a contraction mapping. So it's continuous with respect to the metric on Z5, the standard Euclidean metric. But it's not continuous as a digital function because this P1 is going to P2, and that means this adjacency will be broken when you do the function, all right? So it is continuous using the metric, but it's not continuous using the digital structure. And so this is a fact that if you have a digital image with a metric, then a function which is continuous with respect to the metric may not be continuous with respect to the digital structure. And this is very strange. So in a digital metric space, the digital properties are like totally separate from the metric properties. It's like they have no relationship between the metric and the digital structure. So I have another open question. I don't know actually the answer to this. And maybe somebody already did this in some papers that I just don't know about. But I wonder, are there any theorems about digital metric spaces which use both parts? Both parts, I mean, the metric and the digital. Not only just a theorem about metric spaces, and also not only just a theorem about digital spaces, but some kind of combination of those. Actually, I don't know of any theorem like this. I've seen many papers about digital metric spaces, but it's usually all about the metric. So it's interesting. Again, maybe there are some theorems, I just don't know them. But this is something interesting to look at. Maybe there are some. Okay, so so far we've seen the fixed point property is impossible for digital images. Approximate fixed point is more interesting. Metrics might not be useful for anything. I don't know, because it's hard to combine a metric with the digital structure in a meaningful way. Here's something which you can do. The fundamental group. This is the only time when I'm going to talk about something from algebraic topology, but I'm not going to say too much about this. The digital fundamental group. This was defined in 1989 by Kong, and then later on it was kind of cleaned up a little and given some new definitions by Boxer, which look more resemble more the classical definitions. The idea is you choose some point in your digital image, and a loop is a continuous function from the interval into your space where the initial point and the final point are equal, so it makes a loop. And Boxer has a definition for digital homotopy, which is a way to see when this loop can be smoothly changed into another loop inside your space. So we can talk about homotopy classes of loops. One big problem you run into is the lengths of loops. Every loop looks like a function from an interval into the space, but the interval can be different for all the different loops. And for maps to be homotopic, they have to have the same domain. And this is a little bit of a problem in the definition of the digital fundamental group. Here's an example. If we have this is my digital image and this corner is my base point, the fundamental group here should be trivial. That means any loop in here can be shrunk down just to the base point. That's what it means for the fundamental group to be trivial. It should be true that all loops are homotopic, but here I have one big loop and one small loop. The small one is a function from the interval from 0 to 3 because it has 4 points. And the big one is from 0 to 7 because it has 8 points. And so they cannot be homotopic because they have different domains. This is a problem that Boxer and Kong had to figure out. And they figured out in 2 different ways. That's the difference between those 2 papers. So the loops are not homotopic. Boxer has a very nice way to get around this problem by you just extend the length of both of the loops by inserting a constant portion. So you repeat the base point again and again, just to make the loops long enough so that you can compare one to the other one. But this, I'm just mentioning this as an example of the way that the digital topology theorems are developed. You try to copy very closely as much as you can from classical topology. There is usually some kind of problem that comes up, and then you have to invent some new ways to get around it. And anyway, if you do this in Boxer's fundamental group, you can define a group operation, which makes the whole thing into a group. And all the usual theorems, most of them at least, are true for the fundamental group that you want them to be. So typically we copy the basic idea of something classical, but we need to change most of the details. That's what it usually looks like. All right, let's talk some more about fixed points, and then we're almost done here. One thing that I studied with Boxer, this is in a paper called something like Fixed Points in Digital Topology, was just accepted 2 days ago. As Siraj just mentioned some things about this paper. So given some x, what numbers can be the number of fixed points of a self-map? This set is called the fixed point spectrum. So you have some digital image and you ask how many fixed points could there possibly be for different functions on this digital image. Like for this one here, there are 4 points, and it is true that the fixed point spectrum is the set of all numbers from 0 to 4. This means the 0 is here. It means it is possible for a function to have 0 fixed points on this set. The 1 here means it is possible for a function to have 1 fixed point, and so on. Actually, it is possible for any number of fixed points from 0 to 4. For this set, you might say this has a full spectrum. That is, you can make any number of fixed points that you want. It's not very obvious, but it's not very hard to prove. It's so small that you can just prove directly, construct. But this one actually is not full spectrum. Here, Boxer and I demonstrated that the spectrum is actually this: 0, 1, 2, 3, 4, 5, 8. So it is not possible to have a function with 6 fixed points on this, and also not possible with 7 fixed points. This is not so obvious, but it's true. For this one, the spectrum is like that. And actually, we have a formula for this. Is a cycle of 8 points. If you can make a bigger cycle, and we have a formula, it always looks like something like 0 up to, if there's n points. I don't really remember the theorem. I think the theorem is 0 up to n over 2 plus 1, and then n. and there's a gap in between. You can't get the other ones. This is weird, and not much is known about how to find this. Like in the paper with Boxer, we didn't really have any fancy techniques. We just sort of, every example is a little bit different, and we just do it by hand every time. So it would be interesting if any of you have some ideas about this, some kind of real theory or real technique to figure this out. We don't really have one. Here's some things that we do know about this set. So when the image is very small, less than 4 points, then everything is easy and we don't really need to talk about that. When it's bigger, these are some facts that we have proved. These are just some theorems from the paper. First of all, the total number of points is in the fixed point spectrum because you can always use the identity map, which fixes every point. So that's easy to see. It's also always possible to make 0 fixed points. That's the thing I said back at the beginning, because no digital image has a fixed point property. So you can always make 0 fixed points. We also showed that it is always possible to make 1. This is the constant map has 1. So that's easy also. This is a little less easy. It's always possible to make 2 fixed points or 3 fixed points, no matter what the image is. But 4 is not always possible. So this is kind of interesting. We also have a theorem that tells you exactly when x minus 1 is in the set. There's some equivalent conditions. So this is something that we actually know very easy to find if x minus 1 is in the set. But other one, x minus 2, we have no theorem about that. Here, another theorem we have, if A is a retract, which means there's a continuous map from X which collapses it onto A, like the ellipse or something, then this will be true. So that's an interesting result that we had. Here's some specific cases. So if you have an interval, this is easy to compute. You can get any number of fixed points on the interval. And even if you have, this is like a box, an interval product with another interval. This one also, this is the maximum number of points. You can get any number of fixed points on a rectangular box. We also have a theorem about the cycle. Oh, this is what I said before. You can always go from 0 up to n over 2 plus 1, and then the whole set, but you cannot get the ones in between there. In general, though, those are very specific and very structured examples. In general, it's hard to compute this set, f of x. For this one, for example, this is, I think, too complicated for our methods. You can try to do this just very specifically, but we don't have a real general method to figure this out. So according to the theorems I said before, you always have 0, 1, 2, 3, and you always have the 38. That's the total number of points here. But what else? I don't know. Oh, also 37, that was a theorem about x minus 1, which in this case is true. So 37 is easy to say. But beyond that, it's hard to say. I think actually for this example, it's all these numbers, but I don't know for sure. It's hard to say exactly. I think it's likely, as we go into the future, I think digital topology will come to focus on approximate fixed points rather than fixed points for some reasons that I said before. Although we don't really have theorems about approximate fixed points yet, but I think really this is where the future is for fixed point theory in digital, in this kind of digital topology. I think fixed point theory will be about approximate fixed points rather than fixed points, exactly fixed points. And nothing at all is known about this. You can do the same kind of thing. Ask about what are the numbers which can be the number of approximate fixed points. No, as far as I know, nobody has done anything like that before. I think maybe it's possible that theorems will be easier to prove for approximate fixed points than normal fixed points. So maybe this is easier than what I did with Boxer. I don't know. Next time, Sirajo asked me to try to say something about Nielsen theory in digital topology. So that will be on Monday. Is that right? Yeah. All right. So and like I said, all of this to try to copy Nielsen theory, it all will involve approximate fixed points, not ordinary fixed points. All right. I hope you come back next time. Almost everything I say will be a conjecture next time because it's all. All right. Thanks. That's all.